Yeah, physics is another one of those ones I keep playing around with teaching because it really helps you get that second perspective on what bodies of knowledge are out there and how they all tie together and what premises each field relies on. So, first off, I'm going to record all the lectures and they're going to be on my YouTube page. Now, I already have a Discrete Math playlist, so I'm just going to have another playlist called Discrete Math 2020, and obviously it's going to be the playlist that doesn't have a bunch of videos in it. It's going to be the playlist that only has one video in it. So you should be able to figure it out. Kind of like the classroom we were in was the one that I was in. So if you're in a classroom that I'm not in, you're in the wrong classroom. If you're in a playlist that has, 26 videos, you're in the wrong playlist. Make sense? Alright, I'm going to start by going over the syllabus. Make sure we understand it. Okay, so first off, contact information. I think you all have my contact information, but it's on there regardless. If you need to get a hold of me, just text me. I prefer text to email. I hardly ever check my email unless someone reminds me to, so text me if you need me. Don't try to go through any other medium like Facebook or Snapchat or I don't know. I'll never get back to you. Maybe sometime around Christmas when I check to see if Dad's family's doing something for the holidays and I'll realize you messaged me. Okay, grading. So 50% of your homework, or 50% of your grade comes down to homework in this class. And there's a reason I'm being so nice to you there. The reason I'm being so nice to you there is because this is going to be a proofs-heavy class. And there is no surefire, guaranteed way to prove something. I guess you guys are all familiar with proofs at this point, right? You've all done several proofs. Some more than others. Laura, I see you up late at night. It's weird. Do it less. Anyways. So there's no surefire way to prove something, and so it's very possible when you go and you sit down to do a test or something like that, I give you a proof, and even though you understood all the material that we've covered up to that point, you just can't figure out the trick, the idea that you need to solve that one proof. And so it's very possible that even though you're keeping up with the class and you know a reasonable amount of the material past the class, you're still not performing that well on the test. So that's why I make homework so generous, homework so nice. Now this class, also, you're going to get a ton of homework early on. The homework in this class goes like this as the year goes on. So it starts out very hard, very fast, tons of things to prove, tough. Deal with it. You got to do it. You got to keep up. And it's going to get easier as time goes on, and that's just the nature of the class. Well, it's somewhat by design, somewhat the nature of the class. Part of the reason I try to force it to be that way as much as I can is at the end of the year, kids are just burned out. You're done. You don't care anymore. I can't get you to care anymore. It doesn't matter how many times I do a somersault. You'll all still be asleep. It's crazy. So part of that's for you, and part of that is just the nature of the class. So you need to do the homework. You've got to keep up with the homework. I don't accept late homework. So get the homework done. It's 50% of your grade, so if you don't do it, game over. You've already failed. May as well give up. And you don't want to give up this early. That looks bad. Your friends will laugh. They will point. There will be rumors. So you don't want that. So keep up on the homework. Do it all. Turn it in next time. And I'm always open to go over homework questions if you get stuck on anything. And then tests are 30%. At the end of each chapter, we're going to do a test in class. And then,
Donnie, how do you grade the homework?
how do I grade the homework? That's a great question. So, grading homework is a pain when you're grading proofs. Because I can't just check, oh, did you get the right answer? Because you can just write the last sentence and say, ta-da, it's proved. No, that doesn't mean you proved it. You can't just write, therefore, a squared plus b squared equals c squared. Pythagorean theorem, done. No, I have to look everywhere in between. I have to follow the logic of what you were doing, make sure you didn't break any rules, make sure it logically follows. And so that's a really hard thing to do with these problems. And so I can't just look at your answer. So Typically, I have a deduction system. Each problem is initially worth 5 points. I minus 1 point for minor mistakes, meaning you used a wrong symbol somewhere, or the equivalent to, like, you left a negative sign off somewhere when you were doing a math problem, stuff like that. So that would get you minus 1 point, really small mistakes. At minus 2 points if it's fundamental logic error. Like, no, that doesn't logically follow what you did. You misused a theorem. Like, maybe the theorem says A implies B, and you accidentally used B implies A, but you still proved it all out. So a basic logic error, that's something I minus 2 points for, as a general rule. If it's just a logic error in there. If you have a few logic errors, that's going to be minus 3 points, and you're going to get to minus 4 points if you flat out went off in the wrong direction, la la land. Right? Sometimes I have people, you're supposed to prove this, and they go off and they prove something completely different. It's like, well, I'll give you a point for that. You proved something, that's awesome, but now I can get you very many points. And then you get minus 5 points if it's obvious you have no clue what you're doing. It's obvious to me that you're just putting nonsense on the paper and none of this logically follows with anything, that's just 0 points. You know how the teachers always say, well, if you don't know how to do it, just guess. On this, if you don't know how to do it, there's no point trying to write a proof.
So
there's some problems where the answer is like numbers and stuff like that. And on problems like that, go ahead, guess. But yeah, if it's a proof and you have no clue where to start, where to even go, what definitions to apply, what theorems to apply, and you just start guessing, it's going to be very obvious to me. So, no A for effort.
Questions for your homework, can you bring questions that you have literally no idea how to do?
Absolutely.
Ask them in class?
Absolutely. So you get stuck on a problem, bring it to me, we'll discuss it in class, and then you can fix it right there as we're talking, or whatever. Yeah. So I technically won't take homework until the end of class, unless you want to give it to me sooner, but just need to get it in class. Okay, so we go through, we're going to have in-class tests at the end of each chapter, and then, oh, I didn't have to make the midterm take home. I thought I had to do that. Never mind. So, and then you'll have a midterm and a final. So you'll notice, so tests are 30% of your grade, and then your midterm is what you're going to take at the end of first semester. And that's going to be 20% of your first semester grade, your midterm.
Okay.
And then you're going to take a final at the end of the year. That's going to be 20% of your second semester grade. Okay? Now, that is not comprehensive. So your midterm will only be on first semester material, and your final will only be on second semester material. Does that make sense? So I won't take finals from final questions from first half semester material. And then when it comes to creating tests, I'm either going to use homework problems, or at the end of a chapter, there's test prep questions. So the author specifically made questions for you to study to make sure that you understood the material of the chapter. It's almost like he's saying here, I recommend these as test questions. So I'll either use those questions or homework questions on my tests. And I don't know ahead of time which questions I'm going to use because I do that randomly the day before. I just generate it. But I'll make sure to get an even distribution for different sections, so there's no chance that a test is completely on section 2 and completely overlooks section 1 and section 3, unless section 1 and section 3 happen not to have any homework problems. So that's how the test works, that's how the midterm is going to be, final is going to be, and then extra credit. You'll notice under every homework it says extra credit and gives you an extra credit problem you can do. That extra credit problem can give you an extra 5% boost. So each of your homeworks, when it's all said and done, it's worth 10 points in my system. If you did the homework problem here, if you did the extra credit problem, then you can get 11 points out of 10 on the homework. And since homework's weighted 50%, that averages to an extra 5% on your grade. Make sense how that works? That's the only extra credit I allow. If you got an 89 point 26514 whatever at the end of the year, and you're like, can I get some extra credits or just bump this up? No, you can't. You're worried about that bump, worry about it now, start doing the extra credit now. Okay, any other questions about the syllabus?
Oh, what do you bring to class?
Huh?
What do you want us to bring to class?
There's this really squishy thing that you usually keep in your school.
I don't know if I have them.
Find it and bring it. You were born with one, so hunt it down. Maybe your mom stole it, I don't know. Go looking. It's somewhere. Check her purse. Okay. There are some problems as we get going, some counting problems where a calculator could be useful. We'll talk about those as they come, but normally if you have to do something like 2 to the 19, I don't want you to figure out what that number is, I want that to be your answer. If you come up with an answer that's 179 over 27, I want this to be your answer. I don't want decimals, I don't want a mess, I want clean, concise answers. Answers where it's obvious how you got there, help me grade. This gives me a lot of information about how you came to that number. If you just write some big old number out here, that doesn't help me at all. And then I just have to manually check, and then I can't help you either. Because you might have accidentally, when you expanded this out, you might have accidentally written it wrong, maybe. And then all I know is you got the wrong answer, and I don't know that you even did this. So you had it right, you had a perfect answer, then you accidentally made a mistake plugging in the calculator or whatever, come up with the wrong answer. You don't show me this, you just show me a wrong number. It's like well, if that's all you write, this was the answer, and you just wrote a wrong number, sorry, what can I do? So help me help you. Show your work. Show where things came from. It helps me make sure, oh, you just made a small mistake, not a big mistake. Okay. Any other questions about the syllabus? All right. Then we'll jump into the class, discrete math. Now, why am I teaching discrete math here? No other high school that I know of offers discrete math to students. Why on earth am I offering a discrete math class to students? And those of you who have heard me ever talk about geometry at Masada know perfectly well why I'm teaching a discrete math class. What did you learn in geometry? Exactly.
Yeah.
So geometry has been utterly butchered in the way that it's taught by schools, because more and more they're thinking, okay, what are the real world applications of geometry, is what they keep asking themselves over and over again. And so then they just try to give you the formulas that are geometric formulas that you might come across in real life and teach you how to use those formulas. And that's what the whole focus on geometry has turned into. Trying to teach you how to solve geometry problems that might come up in real life. And they completely miss the point of geometry. The point of geometry was to teach you how to deduce the logical implications of some given set of assumptions. We're talking about Hilbert's axioms. I think that there's 20 of them. What are the logical implications of these 20 axioms? Do you understand what I mean by an axiom? A basic assumption of the field. It's not something you prove. We say, well, assume it's true, and look what else is true if this thing is true. That's what geometry was about. It was about training you to logic and deductively reason. Geometry was just the medium. It wasn't about learning how to solve geometry problems. Anyone who can prove geometry isn't going to struggle solving a couple geometry problems. That's not the case. So you get that for free. That's a natural byproduct. If you know how to do geometry, you know how to solve geometry problems that come up in life. But that wasn't the point of geometry. The point of geometry was to teach you to logic and deductively reason. That was the point. And more they're missing this point. And more as education keeps changing more towards applied math versus teaching you the theory behind math, you get exposed more and more to numbers and less to geometric figures. So chances are you are all far more comfortable with working with something like the number 19 than you are with working with a line segment. Once I show you a line segment, you naturally want to say, yeah, but how long is it? What's the number I should put to that line segment? And you want the number there. When really a number is a far more abstract concept than a line segment. It's just that you've been trained with numbers and numbers over and over again, and arithmetic over and over again. And so it just so happens that even though geometry is a lot simpler than algebra, you're far more comfortable with the algebra part. So what I wanted to do was utilize on the fact that you're already comfortable with the algebra part. You're more comfortable with algebra than you are with geometric figures, and teach you that same thing. Go back to teaching you how to determine the logical implication of some given set of assumptions. Teaching you how to deductively reason. That's the reason I'm doing this class. And that's the reason I'm teaching you guys now. So, this is what we'll focus on. Deductive reasoning now. We'll have a quick high-level conversation about reasoning. Some of you have heard it a lot, some of you not so much. We'll have the conversation real quick. So reasoning, first off, what does it mean to give a reason? It's your justification for some conclusion. That's what a reason is. What's the reason you did that? You start lying to your parents, coming up with a story. That sounds like it justifies it, right? That's your reason. Terrible, but it's your reason. So we can use different types of thinking to justify our conclusion. Now, in math and logic, the reasoning that we use is called deductive reasoning. It has to be a logical implication, and we'll get to exactly what we mean by a logical implication here in a second. But to help you get the intuition for it, the common example is the statements, Socrates is a man, and all men are mortal. And then the conclusion you can draw from those two is what? Socrates is mortal. And so, the way we would say that in terms of math, we'd say, if Socrates is a man, and if all men are mortal, then Socrates is mortal. That's the way we say it in math. We'd say, if these two are true, then this is true. We do not say that this is true. We do not say that this is true. We say that if this is true, then this is true. That's what we're saying is true. We're saying the implication, if we call this top part A and this bottom part B, we're saying A implies B, that whole statement, this whole statement is what's true. We're not calling A part true. We're not calling this part true. This is called the antecedent. We're not calling the antecedent true. We're not calling this B part, that's called the conclusion. We're not calling the conclusion true. We're saying that the fact that the antecedent implies a conclusion is what's true. That's what we're saying in math. It's very precise what we're saying, and we're talking about, we show, those of you taking logic, we show that these are tautologies. Not only are they true, they're always true. They're universally true statements. If any statements we can comprehend of as being true are true, mathematical theorems are true. It's knowledge to the extent that you can obtain knowledge. If you can call anything true, you can call these things true. So let's contrast them really quick with some other things you might say are true. Tell me one thing you know is true. Look outside. Something occur to you?
It's cloudy.
It's cloudy. You know that's true?
No.
Yeah, cloudy might be a little vague. What about the sky's blue? Anyone know the sky's blue?
Yeah.
I'm going to have to go get some first grader, bring him in here, and ask him, you guys. Raise your hand if you know the sky's blue, and blow that poor kid's mind. Is the sky blue?
Yeah.
No? Then what color is it? So you feel pretty, you ought to, you're worried because I'm up here asking you questions, but if someone else asks you, it's a sky blue, you'd say, obviously, right? But is the sky blue? Or the sky is blue. That's a statement that most people would say, and they say, I know what that statement means. And some years I've done this, I would ask that question. Well, I would ask, what do you know? And someone would say, the sky's blue. That's a common one that comes up. And then I get a really narrow in on it, you know? And I say, oh, you know that? Yeah. You sure? Yeah. You positive? Like, you know that as well as you know anything? That's the thing you're most confident of? Yeah. Okay. What's blue?
It's a color.
And that doesn't tell me what blue is. Red's a color, so blue's red. Blue is color. Color is red, or red is a color. Therefore, blue is red.
It's a frequency.
Yeah, getting a little closer. And the other part of that, the sky is blue. Is my finger in the sky yet? Tell me when to stop. Did I get there? No. No? Gotta keep going? What's the sky? When do I get there? So these are very ill-defined terms in common notion. We could come up with a mathematical definition for blue. We could say we have this mathematical model called a photon. One of the ways we can model it is a wave. One of the properties wave have is a frequency. And if the frequency is in this range, we classify it as blue. And yes, if we build up a mathematical model, we can then have it well-defined what we mean by blue. So that's one way to do it, but most people don't have that definition in their head. They just have this vague notion, same with this vague notion of what the sky is. And so you don't even have precise understanding of what the statement the sky is blue is even saying, let alone the truth value of it. It's not even entirely clear what exactly that statement's saying. And so we need to be very precise in the things that we're talking about when we're talking about math and logic. We can't have any of that ambiguity. We can't go around pretend to know what blue is when we don't know what blue is. We can't go around pretending to know what the sky is when we don't know what the sky is. If we can't define it, we can't claim to know what it is. Make sense? Kind of took a leap there, huh? Okay, so we talked about deductive reasoning, logical implications, statements that are universally true. Another way to think about how these statements are true is they're in no way contingent upon the facts of this universe. It does not matter if you know who Socrates is, that he's a person. It doesn't matter if you know anything about Socrates. It doesn't matter if you know anything about men. And it doesn't matter if you know anything about mortal. If you know that you could say blah instead of Socrates, blah is a doe, and all does are pink, then blah is pink. You don't need to know what those words actually mean. You don't need to know exactly what that is, and yet you can still say this statement is for sure true. It's in no way contingent upon facts of this universe. Get rid of this universe, all of math, all logic, still true, just as valid as it's always been, always will be, always has been. Okay? Then, inductive reasoning. Inductive reasoning is the reason that you think that when I let go of this marker, it's going to do what?
Fall.
Fly, right? No, fall. That's what it always does. It falls. And if you carefully measured, you notice it falls at roughly 10 meters, it accelerates downwards at roughly 10 meters per second squared. And why do you think that when I let go of this, it's going to fall?
Because it has over and over.
Why do you think gravity works?
Because we've experienced it over.
Because of your experience with it. You've seen over and over again, every time you let something go, it falls. That's happened every time you've tried it, right? In fact, not every time you've tried it, every time a person anywhere has tried it. That's pretty crazy. Therefore, it must always be true, right?
No.
How many times do you have to test a theory to know it's always true? Once?
No.
Twice?
Can't say it's always true.
What if you come up with infinite examples of it being true? Are we finding good and we can say, okay, that's proven?
No.
No?
There could exist what
After infinite examples?
Yep.
What's more than infinite? So we've handled all the examples. Okay, infinite different examples. So we're not doing the same thing over and over again. Then we've proven it for sure, right? You guys are really hedging your bets more than any other class.
We know you do it.
And you're right. Infinite examples still doesn't prove squat. Not here, but we definitely view it as useful down here in science. So in math, if I were to tell you every number is even, and I can prove it, check it out. I can give you infinite examples. Tell me how many examples you want. I can give you infinite examples. Therefore, every number is even, right? There's infinite numbers. If I give you infinite different examples, I've handled all the numbers, obviously. No, it can't just be true 100% of the time that you've tried it to be true here. But here, in the real world, in science, in this universe, when we're doing science in this universe, we don't have the benefit of being able to just prove that when I let go of this, it's going to fall. That's not why you thought that this was going to fall. It's not why you think the sun's going to come out tomorrow. You think it's going to happen because that's how it's always been. And so science starts out by making these observations and saying, every time we've watched this happen, it's happened this particular way. Right? Every time I've dropped this object, it's fallen this way. Every time I've dropped it over here, it's also fallen that way. Everywhere I go, every time I try it, it falls this way. And then so scientists make a generalization. They call it a law of physics, or a natural law. I don't know how you're used to hearing it. But it's a generalization. It's saying, every time we observe this phenomena, it's happened this way. So you see a bunch of different instances of the same phenomena, and then you make a generalization based off of it. So you're going from instances of some phenomena occurring to creating some generalization, some law. And that's the foundations of all science. I would go into this pyramid. So that's the difference between deductive and inductive reasoning. Deductive reasoning, it's impossible to be false. Inductive reasoning, every time we've observed it, it's true. See the difference?
Yeah.
Abductive reasoning is the third type of reasoning, and this one's the counterpart to inductive reasoning. Inductive reasoning, you go from watching a bunch of phenomena to creating one generalization. Abductive reasoning, you take all your generalizations that you have, and you try to reconstruct a specific phenomena. So, give you the common example I like to give. So, you leave a toddler in a room with a chocolate chip cookie right there in their reach where they can get it. You walk outside the room, stand outside the door, wait a couple minutes. You come back in the room. You see the toddler standing next to the cookie. There's chocolate smeared all over his face. The cookie's gone. Chocolate smeared on his face, crumbs everywhere. What's the conclusion?
He ate the cookie.
The toddler ate the cookie, right? Now, for all you know, Laura was in the room. She was hiding in the closet. As soon as you left out, Laura comes out of the closet. She eats the cookie, saves a little bit, smears it on the kid's face, spills crumbs everywhere. It's making a nice big mess. And she comes back, hiding in the closet. Right? Sneaky.
It's always weird.
Poor Abby gets blamed. Again. Anyways. So that could obviously be false. It's not that every time a toddler's been left in a room, that the toddler's eaten the cookie. That's not some law of nature that we've observed. You have to use abductive reasoning. You have to take all your generalizations, all your things you know about. Typically when I don't see anyone in a room, they're not in a room, you take your generalization that, I don't know, typically when kids are left with food right there where they can reach it, they end up biting the cookie or whatever. You take all your generalizations to try and recreate this one scenario. It's often what we have to do in history. It's how we put together some particular event in history. We take all our generalizations, everything we know about science, everything we know about other historical facts that are accepted to be true, to try and recreate this one scenario. And it's also what you use, it's also a type of reasoning you have to use inside a court of a law. So, if you were to then go take the toddler to court, charge him for eating your cookie, all you have to do is prove beyond a reasonable doubt that they ate the cookie, and then the kid gets sent off to jail. That's the requirement that we have for a court of law. You have to prove it beyond a reasonable doubt. If you prove it beyond a reasonable doubt, then it's considered proven in that case. Now, that's not near as good as proving some scientific theorem like Einstein's general theory of relativity, which isn't near as good as proving some mathematical theorem like the Pythagorean theorem. Pythagorean theorem, general relativity, toddler ate the cookie. We can prove all those things, and we prove them in their different fields, but what it means to prove them is fundamentally a different thing. Make sense? Okay. So, let's jump into some example problems to help you get a feel for the types of problems that you're going to have to do in this class. So I told you in this class that one of the challenges is there's no surefire way to prove something. And oftentimes, if you're given a problem, you just got to come up with a trick for solving the problem. And then it's like, oh, that's how you do it. And then you solve the problem and you move on. So I want you to solve this problem. How many of you already know the answer? Okay, good. So I want you to solve this problem right here. And this will give you some insight as to how you do the problem. And if you figure it out, don't tell anyone. Let them think about it. But start working on it.
As multiplication?
Yeah. X minus A times X minus B times X minus C all the way to X minus Z. What is it? Well, first off, it's going to be X to the 26, right? Minus, and you keep going from there. And we're going to have some big answer. Fill up the whole whiteboard with your answer. So get going. I'll be back. I need some more. Help to start writing it out. Do you understand what I mean by the 3 dots here?
Yeah.
Yeah.
Okay. So start writing it out. Come on, don't be so lazy. My goodness. So you fill up a couple pages, no big deal. So you missed the start, but
Yeah, so
I record all my lectures. So I have a page on YouTube. If you just search Donald Timpson, you'll find it.
Right.
I'll have a series up by the end of today called Discrete Math 2020. And then this video will be uploaded so you can catch up on the first part. Fortunately, you didn't miss a lot of the actual content in the book. And I'll get you the book and the syllabus. Let's see. No cheating. Raise your hand if you have it. Oh, never mind. Why did I set down my copy of the syllabus?
I think it's under your computer.
Ah, good call. Okay, and then I just sent you the syllabus and book to your Gmail, so I think it was a Gmail. Yeah. Staffers Hammond at Gmail.
Yeah.
Okay. So send it there. Let me know if you get it. Make sure you got it. Do you have a way to check that?
I have my phone.
Yeah. Feel free to check it. Make sure you get it. No point if you don't have the book and syllabus. Oh, email my account.
Oh yeah, I forget the email and that is faulty in the gradebook. So it's gonna be a different one. Do you want me to give it to you right now?
Yeah. 1 second. Let me look at that. Okay.
It's Stafford Hammond, but Hammond is spelled with 3 M's. No. 3 M's, yeah, and 1 N.
At Gmail.
04@gmail.com.
0404. Anyone got it?
No.
I'm afraid not.
So we're trying to solve this problem. And the motive for solving a problem like this is to give you a sense of what problems in this class are going to be like. So to be very upfront, this is going to be a difficult class. It's not going to be easy, it's going to be challenging. And you're going to typically have to think in this kind of way where you've got to come up with a trick to solve the problem, and the problem's just a pain until you figure out your trick to solve the problem, and then it's just, well, that was easy. No, you can't do that. Someone's breaking algebra over here. So I'll give you a hint as to something you can't do. If I have x minus a times x minus b, that is not equal to x times a times b. Or whatever you had.
Oh, shit.
X minus a times b. Okay, that is not equal to x minus a times b. It is in fact equal to x squared minus ax minus bx plus ab.
Yeah.
So, yeah, that was only 2. So, you gotta expand out the 26 for the alphabet. Get cranking.
Yeah, no. But I feel like
Start by writing out the expansion. Stop being so lazy.
That's not being lazy, that's just like being intelligent.
Is it? How much progress have you made? In the meantime, you could have easily had that written down.
Easily, huh?
Written out the 26 terms? Yeah. Doesn't take that long to write out 26. Took me 4 seconds to write out 4, so 26 seconds to write out 26. That's not so
why
bad.
did you say plus a?
Huh?
Why is it plus a? Negative.
What's negative a times negative b? I'll give you a hint. It's not negative c.
Still not getting that email.
Still no email? Oh, it came back bad. Address not found.
You tell them that M was someplace in the other.
Stafford. Why did that one autofill?
Oh, it autofill?
Well, one of them did, but I could just be using my history, but it only autofilled one of them, not the other, and it doesn't have any typos. STAFFORDHAMMON.
There's no O. There's an M in place of an O.
Oh, no,
No, don't ask how I made such a stupid mistake.
Okay, that makes sense. And then you said 04
Yeah.
at Gmail? Let's just do a quick test before I upload all the stuff. So let me know if you get testing now, and then I'll upload all the stuff. and send it to you.
There's 2 X's now.
No helping.
I just got it.
Awesome. Okay, this is uploading, and I'll send it. Raise your hand if you got it. Okay. Hey, eyes on your own paper. Okay. So what was the trick to the problem, Leah?
It's x minus x. Which
Right.
is 0.
One of the terms is x minus x. What's x minus x?
0.
Was 0 times anything?
0.
So it's equal to 0.
That's why he said don't help anybody.
How to get x minus x?
Because there's
X minus c, x minus d, x minus e, x minus f. Eventually get x minus x minus y, x minus z.
Yeah.
So one of them is an x minus x, which is 0. 0 times anything? 0. Right? We proved that in logic
Yeah.
just the other day, so you're well familiar with that fact. And there you go. See, so you understood, well, most of you, understood all the rules with how to multiply this out. You understood all the algebra, you understood all the rules, and yet you couldn't solve a relatively simple problem. And you got stuck on it for a while. And there's no guarantee, even if you perfectly understand algebra, that when I give you this problem on a test, that you're going to be able to come up with that answer 0. This is exactly why I make homework such a big part of your grade. Because even if though you perfectly understood all the algebra, you can still get stuck. So that's what this is supposed to be an example of, is a problem that you can easily just get stuck on until it just clicks, then it's easy, right? And once you know how to do this problem, you're all like, oh, duh, yeah, that's so easy. Now you can solve this one type of problem anytime it comes up. But the problem is you're only going to get it once and then we move on. So being able to solve this problem doesn't help you down the road. It was just helping you develop that type of thinking, looking for those solutions. So there you go, nice little frustrating problem for you to bang your head against. And your first homework problem. You're welcome.
Yeah.
Okay. So now let's talk about definitions. So you remember, as we were attacking the statement, the sky is blue, we can take a lot of issues with that statement and show that someone making that statement has no clue what they're talking about, right? Went my finger in the sky. Is it there yet? Is it there yet? What's the sky and what's blue? That's not those aren't well-defined terms. When people typically say that, they're not positive what it is they're saying. So we need to have precise definitions, know exactly what we're talking about. So let's give you an example of a definition, one that we're going to use in this class all the time. Even. An integer is called even provided it is divisible by 2. Right? Now you all understand even perfectly? Because I gave you that perfect definition. You're welcome. No! There's a lot of issues with this. What the heck do I mean by integer? What the heck do I mean by divisible? And if we're being real picky, what do I mean by 2? These things are not defined in this definition. Now, we need to start somewhere with you guys. We can't start at the foundations of math and work our way up, otherwise we finish a whole year's worth by the time we were ready to start this class. So we're going to presuppose some stuff in this class. Some of the things we're going to presuppose you already understand is what addition is. I know, scary, but we're going to assume you know how to add numbers. We're going to assume that you know how to multiply numbers. We're going to assume that you know what I mean when I say a positive whole number and a negative number. We're going to assume that you understand what less than or equal than, greater than, and greater than or equal than mean. And I think those are pretty much what we assume. So we're going to assume that you know that, and we're going to work from there. So we're going to assume that you know what 2 is. And you might still take a little bit of issue with, well, are we positive what integer is? And you should definitely take issue with divisible. What the heck does divisible mean? Right? So, what's in, oh, okay, we already said that. So integers. What are the integers? First off, I'm going to use this fancy z, the z with an extra line, to represent the set of all integers. And what are the integers? They're any whole number, positive, negative, including 0. Okay? These are the integers. Any question about the integers? How many are there?
Infinite?
A lot. Yeah, there's infinite. Okay. Divisible. Now let's come up with a precise definition for what we mean by divisible. And I'm assuming you know what 2 is. Sorry, just have to. Okay, divisible. So let A and B be integers. So now we're talking about 2 things in here. We know what these things are, so now we know what A and B are. There are 2 things in there. Let A and B be integers. We say that A is divisible by B, provided that there exists some integer C such that B times C equals A. It's a mouthful. These definitions are often going to be a mouthful, and oftentimes you just need an example to help it click in your head what exactly it's saying. So we'll look at some examples and we'll go back up to the definition. So maybe finish the definition, do examples, and back to definition. So let A and B be integers. We say that A is divisible by B, provided there exists some integer C such that B times C equals A. Remember, I'm assuming you know what times means. We also say that B divides A, and we write it B divides A. So that's how you read this. B divides A, or A is divisible by B, are 2 ways of reading this right here. So we're defining what exactly this means when you see this. So here's the definition of what exactly it means. Let's look at some examples and go over the definition again and make sure we clicked it in your head. So, true or false, 4 divides 8.
Yeah.
So if 4 divides 8, that means that there's some integer, C, there's some integer, such that 4 times that integer equals 8. What's the magic integer? 2. So since there exists an integer such that 4 times that integer equals 8, then 4 divides 8. Alright, what about 8 divides 12? True or false?
False.
False. There's no integer I can multiply 8 by to get 12. Right? 3 divides 9?
True.
True. What's the magic integer?
3.
3? That one's pretty magic. Alright. 2 divides 5?
No. False.
False. 0 divides 1?
False.
Okay. 1 divides 0?
False.
Okay. How can something big divide something smaller than itself?
Well, there exists an integer C, 0.
The magic integer 0. 1 times 0 equals 0. Yes, 1 divides 0. Any number divides 0. 2,546 divides 0. There exists some integer, C, such that that thing times C equals 0. So pay attention to what exactly the definition says. Don't rely on your own weak intuition. Carefully read the definition. Try and apply the definition the best you can. See if it holds. So let's read the definition one more time. I think we'll have had it. Let A and B be integers. We say that A is divisible by B, provided that there exists some integer C. When I do S dot T dot, that just means such that B times C equals A. You feel like you understand the definition now?
Yeah.
So if I were to say something like, prove 8's divisible by 4, you know how to do that. You say, observe 2 times 4 equals 8. Therefore, there exists some integer, namely 2, such that 4 times 2 equals 8. Easy peasy. Squeeze a lemon. Okay. Moving on. Odd. So, we have a definition of divisible. We have a definition of even. Now we know what even is, notice. So, even means it's divisible by 2. So, is 4 even?
Yeah.
How do you know?
Because there's 2
Because 2 times 2 equals 4. Is 8 even?
Yeah.
How do you know?
Because 2 times 4 equals 8.
Perfect. Is 5 even?
No.
No.
How do you know?
Because there's not a number times 2 equal 5.
There we go. I want you all in sync. That was perfect. All right. So that's even. And then what's odd? Odd is just a number that's not even, right? No. No. All right. So let's go over what odd is. An integer A is called odd, provided that, now some notation for those of you who haven't seen this, because I'm really lazy in my writing. Provided that backwards E, we read that as there exists, x in the integers. That's how we read that. Alright? Provided that there exists x in the integers, or another way we can say that is, provided that there exists an integer, namely x, such that a equals 2x plus 1. So if I can find an integer x such that 2x plus 1 equals a, then a is odd. Okay?
Okay.
Feel like you're kind of getting that?
Yeah.
Sorry about the dense notation. The book will eventually introduce it, but I'm just too lazy to not use it. So, tough life. Okay. So, let's demonstrate some stuff then. Is 19 odd?
Yeah.
How do you know? What's the magic integer? 9. 9 is the magic integer. Since there exists an integer, namely 9, such that 2 times that 9 plus 2 times that integer plus 1 gives you 19, then 19 is odd. Is 57 odd?
Yeah.
Yeah.
How do you know?
It's 28.
28. Someone knows how to minus 1 divided by 2. Whew. 28. 2 times 28 is 56, one less than the thing there. You don't even have to do the math. You can just trust I got the right answer. All right. 48. Is it odd?
No.
No.
Are you sure?
Yeah.
This isn't, we don't necessarily need to be using your, you don't think that there's an integer I can find to plug in here to make 48?
There isn't. Yeah.
Okay, pretty safe. Yeah. All right. What about negative 11?
Yeah.
Yeah.
Negative numbers are odd?
Mm-hmm.
It's -6.
It's an integer. Yeah.
Is there an integer?
Yeah.
What is it?
Negative 6.
Negative 5, right?
No,
Minus
negative
1?
6.
Oh, negative 6. Okay.
Oh.
Yeah, so you'll notice that when you're looking for the integer for negatives, you're going to do one more than your gut naturally wants to do. Right? Because if I were to say do it for 11, what's the number we put here?
5.
5. But when we're doing it for negative 11, notice it's negative 6. And that's how you use the definition. And you have to use the definitions the way that the definitions are listed here. When you have to prove that a number is odd, you can't just say da 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 is equal to 31 and therefore it's odd. That's not how you prove something's odd. Odd doesn't mean equal to 31. It means there exists some integer such that 2 times that integer plus 1, such that you can express it that way. Right? So if you can write a number this way, it's odd. And notice that this is just rewriting a. Some students get stuck on this for some reason. 2x plus 1, that's just a number. That's just an integer. Just like a is just an integer. It's just a different way of writing a. Right?
Are all these definitions in the book? Or
Yeah, all these ones are. We'll do some stuff in logic that I don't really like how the author does it, so I just do it how I want. I do that after I did the conditionals, and I'm like, if he's going to develop logic, may as well do it right. But, anyways. Okay, let's move on. A prime number. What's a prime number? An integer p is called prime, provided that p is greater than 1, and the only positive divisors of p are 1 and p. Right? You're used to prime numbers already? Is 7 prime? Is 4 prime? Good job. Alright, so an integer p is called prime, provided that it's greater than 1, and the only positive divisors of p are 1 and p. And then let's do composite number, because you have primes and you have composites, right?
yeah.
Yeah. So a positive integer a is called composite, provided that there exists some integer b such that b divides a and b is between 1 and a. So let's go over some examples using both these definitions to make sense of it. 3, is that prime or composite?
Prime.
Prime. How do we know it's prime? Its only divisors, its only positive divisors are 1 and 3. Right? 11, is that prime?
Yes.
Yeah, its only positive divisors are 1 and 11. 15, is that prime?
No.
No. Why is it not prime?
Divided by 3 plus.
3 divides it, 5 divides it. So it has other divisors. You just have to find one. Once you find out one other divisor, you're done. So it's not prime. Is it composite?
Yes,
How do you know?
because 5 is smaller than 15.
Right, because 5 is a number between 1 and 15, and 5 divides 15. 5 is the magic integer. There's also another one that you could have used. You could have used 3. 3 divides 15, and 1 is less than 3 is less than 15.
Okay.
Therefore, it's composite. Starting to click?
Yeah.
Let's do another one. 19, prime or composite?
Prime.
Prime. 2, prime or composite?
Prime.
That's even.
So,
So, good answer. 1, prime or composite?
Neither.
Prime, right?
Oh, yeah.
Yeah, because it's greater than 1, just like the definition requires. No! It's not prime, and it's not composite. It's neither. There's no rule that says a number has to be either prime or composite.
Okay.
We good with how 1's neither?
Yeah.
Okay, what about -7?
Prime.
Prime! Because it's greater than 1.
Oh.
Ah! So that makes it composite.
no.
Alright, pay attention to the
Forget my
definitions.
next definition wrong.
Alright, pay attention to the definitions. Okay, 16.
Composite.
You sure? Okay. And how do you know it's composite?
2.
2 works. 2 divides 16, and 2 is between 1 and 16. Let's do one more up here. -16. Prime or composite?
Neither.
Why can't it be composite? 4 is between 1 and... Oh, shoot.
It's a positive integer.
Oh, and a positive integer. But A, we already have is greater than 1 here, so. Okay, we good? Feel like we understand the difference between prime and composite?
Yeah.
And so every integer is either prime or composite?
No.
No. There we go. You're paying attention to my words rather than my tone. That's great. Okay, so there's some examples of definitions. You'll be doing basic things with those definitions in your homework. For you, should have specified. You're going to get a ton of homework to begin with, and as the year goes by, it's going to drop off like this. And we don't do late homework, so you got to just keep up in the class. This is one of those classes that if you get behind, tough luck. There's no way to continue if you don't understand the previous material. It just builds on itself. Kind of. Don't tell them that's not the truth. Anyways, lots of homework to begin with, but it does get easier as the year goes on. So just give it a good push to begin with, and as the year goes on, it'll get easier and you'll be fine. Especially at the end of the year, it gets real easy. So moving on, theorems. So the core of all math, I mean, we have our definitions that we construct, but the core of math is just proving theorems. Proving theorems. That's all we do over and over again. That's the heart of what math is. So it makes sense to try and understand what exactly a theorem is. And before we talk about a theorem, let's just talk about a statement. Because ultimately we want to say that a theorem is true. We want to say something like the Pythagorean theorem is true. We talk about theorems as being true. We prove them means show that they're true. So they have to be something that can be true or false. So they have to be what we call statements. What's a statement? A statement is a sentence that's either true or false, but not both. Rhoda is wearing a purple shirt. That's a statement. It's either true or false. Right? I am the king of the world. That's a statement. It's either true or false. Every single one of these, that's a statement. 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 The important point that students get caught on and have gotten caught on in the past over and over again. This is not divides. This is not a different way. If I had something like this, even though that statement is not true, that is not, here's one that's true. This is not a different way of writing 1. Okay?
1?
Yeah. If you're like, why would that even make sense? Perfect. You're right with me. But people in the past, they wanted to treat that divides as a divided by sign. As the class goes on. That is not a divided by sign. This isn't an operator. We're making a statement. You understand the difference between an operator and a statement? An operator takes two numbers and spits out a number. This is not taking two numbers and spitting out a number. It's stating a fact. Saying 8 divides 8 is a fact. That's true. You can call this true or false. Is this true or false? 2 times 4.
You can't.
Yeah, that's not a statement. So there's a big difference between applying an operator and a statement. Good? So don't go treating that like device. Okay. So we got a feel for what a statement is, and we got some basic types of statements that we're interested in math. So, theorems. What's a theorem in math? It's a statement which we have proven to be true. We know that the statement's true. We've proven it to be true. That's what we mean by a theorem. Roughly. We'll get into the nitty-gritty of what exactly a theorem is more. A conjecture. Oftentimes you'll hear about conjectures in math. As the textbook goes on, you'll be asked to formulate your own conjectures. Conjectures are statements that you think are true. We haven't proven them to be true, but we also haven't shown that they can't be true. So we just think that they're true. And so there's a lot of ideas out there that are just conjectures right now that mathematicians are currently working on. That's what a mathematician will often do. They'll look at a conjecture, and then they'll get to work trying to prove it. Something that they think is true. And then there's statements that are false. We have a special name for those. Mistakes. Don't do those. Never make a mistake and you'll be fine. Okay, so let's look at an example of a theorem. Example of a theorem, the Pythagorean theorem, the one you all know and love. What's the Pythagorean theorem? Notice 2 pieces that a theorem usually has. It starts out with if something, where is it? Then something. So theorems are typically of this form, if-then statements. Or another name that we have for these types of statements is called implications. Theorems are implications. So if A and B are the lengths of the legs of a right triangle, do you know what the legs of a right triangle are?
Yeah.
Okay. So if A and B are the lengths of the legs of a right triangle, and C is the length of the hypotenuse, then A squared plus B squared equals C squared. Pythagorean theorem. We prove that in geometry. You all know and love it. You all remember your proofs. Can come back up here and construct it. Okay. And then, I don't know why at this point in the book the author introduced a joke. I feel like he should do it earlier, but he has a little joke to help you get the idea of the difference in precision. So the joke's about an engineer, a physicist, and a mathematician. And they're taking a little cruise and they're going past some islands in Ireland. And the engineer, he's looking off the boat, he looks over on an island and he sees a black sheep. He says, that's interesting. The sheep in Ireland are black. The physicist raises his nose. He says, oh, you poor thing. You make such dangerous assumptions. All we know is that the sheep on that island are black. And the mathematician whispers to himself, or at least half black. Because you can only see one side of the sheep. You see it? Oh no, the physicist says, all we know is that that sheep is black. That's what he says. And the mathematician says, or at least half black. Because you can only see half the sheep. For all you know, the other side of the sheep is completely white. You're making some dangerous assumptions. So in mathematics, we have to be very precise. We can't say most likely, it's probably the case, none of that. We have to know. It's impossible for it to be false. That's what we mean when we've proven it to be true. It's impossible for it to be false. No, we're just really, really sure. Good feeling in my left shoe. That's how we know. Okay.
Sometimes that's how you start a proof show.
Yeah, you have an inkling, and you make some conjecture, something you think is true. And you go about trying to prove it, trying to prove it, trying to prove it. And sometimes you might get stuck, and you're like, and think, why can't I prove this stupid thing? And then it finally occurs to you, oh, because it's not true. I've done that. I've worked a long time on proof that. Turns out it just wasn't true. And it was on a stupid exam, too. So it was a time test, and I'd done like a third of my time into trying to prove this one problem. And it was just, I just need to give a simple counter example to show it couldn't be done. It was really stupid. Okay. So theorems are typically of the form if-then statements. If A, then B. And we typically represent if-then statements like this. A implies B. We read that arrow as implied. A implies B. if A is true, then B is true. Give you an example of some statement of that form. If Donnie's wearing shoes, then he's wearing socks. If that statement's true, then we can say Donnie wearing shoes implies Donnie's wearing socks. In that case, A stands for the statement, Donnie's wearing shoes, and B stands for the statement, Donnie's wearing socks. Now notice that they have to be statements. A has to be a statement. It has to be something that you can call that true or false. Notice Donnie's wearing shoes is something that you can call true or false. B has to be a statement. Donnie's wearing socks. You can call that true or false. And then the whole implication then is a statement. If A is true, then B is true. Which means you have to be able to call the whole implication false. Now how do we know when to call the whole implication false? Do we call it false? Or when do we call it true, in other words? Maybe that's the way to say it. When is this whole statement true? Is it true when A is true and B is true?
Yeah.
Yeah?
No.
No?
Are you saying you could be wearing socks but not shoes?
He's saying if the statement A is true
If
and
this-
B is true.
If I'm wearing shoes and I'm wearing socks, is it true that if I'm wearing shoes then I'm wearing socks?
Yeah.
Yeah. So, we're going to write down our 4 combinations for A and B. We have 4 possible combinations. We can have A is true and B is true. We can have A is true and B is false. We can have A is false and B is true. And then we can have A is false and B is false. So those are the 4 possible combinations that we could have. And we're wondering, when is the implication true? Right? So we just concluded, if A is true and B is true, then the implication A implies B is also true. Right? So now let's look at the next one. Let's say that I'm wearing shoes and I'm not wearing socks. You don't know, maybe I'm not. So let's pretend I'm not wearing socks. Is the statement, if I'm wearing shoes then I'm wearing socks, true? No, it's false in that case. Okay? Now say I'm not wearing shoes at all, but I'm walking around in my socks. Is the statement, if I'm wearing shoes then I'm wearing socks, true?
Yes.
Yes. It's not false.
It's not false. And because of the way the author does this, yeah, he did pick that up really fast. And since the way the author does this, unfortunately, we haven't covered not yet. But you have the right idea. It's not false, and the statement has to be true or false. So if it's not false, it has to be true. That's the perfect way to think about that. And now, let's pretend I'm walking around in just my feet. No shoes, no socks. Is the statement, if I'm wearing shoes, then I'm wearing socks, true?
Yes.
Also not false.
It's not false, which means it's true. Perfect. Okay. So we have a bunch of different ways that we could phrase A implies B. There's a lot of different ways that we could read this. We can read that as if A, then B. If I'm wearing shoes, then I'm wearing socks. That's the same thing as I'm wearing socks if I'm wearing shoes. That's the same thing as I'm wearing socks implies I'm wearing shoes. That's the same thing as I'm wearing socks only if I'm wearing shoes. Oh, I said that backwards. I'm wearing shoes implies I'm wearing socks. I'm wearing shoes only if I'm wearing socks.
Yeah.
Okay. Any of those feel weird?
Well, only if is the same as it?
Yeah. So here's another way to think about the only if. Let's interpret, and I found this one's really useful. Let's interpret A as smoke, B as fire. If there's smoke, then there's fire.
Okay.
Right?
Mm-hmm.
There's smoke only if there's fire.
Mm.
You see how those are the same?
Yeah.
Only if is a weird one, but for some reason that smoke fire, that just works in people's brains. Other examples, it's like, is it? Okay. So that's an implication. When we mean an implication, we mean A implies B. And here's its truth values. If I know that A is true and B is true, it's true. If I know that A is false, it's true. If I know that A is true and B is false, it's false. Right? Left? Up? Down? Pick a direction. Okay. So now let's get to equivalences. Equivalences, or another way we say it, are if and only if statements, is what happens when we combine 2 implications. It's when you have A implies B. This is so dumb that he covers it this way. You know what? Forget the way the author does it. We'll come back to this. Put a break there. Let's go do these and then we'll come back to this. because you should cover conjunction, and we should have covered negation before this stuff. Oh well. So, we're going to jump to here, because that's continuation from here. So we'll come back and do this block after we do these. So don't let me forget about that block. Conjunction. What is the conjunction of two statements? So if A and B are statements, then the statement A and B is their conjunction. Now notice we said A and B are statements, which means you know that A is either true or false, and you know that B is either true or false. And I said that A and B is a statement. The statement A and B is their conjunction. So that means A and B has to be true or false. So let's figure out when A and B is true, and let's figure out when A and B is false. So there's four combinations. We can have true, 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 false, false, true, false, false. And that symbol right there just means and. Forget this column for now. So this, the way you read this is A and B. So if A is true and B is true, is the statement A and B true or false?
True.
True. Let's give it a concrete example real quick. Let's make statement A, I'm holding a green marker. Statement B, I'm holding a black marker. If I'm holding a green marker and I'm holding a black marker, is it true that I'm holding a green marker and I'm holding a black marker?
Yes.
Listen to me repeat myself. Okay, let's do the next row. So we'll make A true, B false. A's, I'm holding a green marker. B's, I'm holding a black marker. We're setting up this case. I made A true, B false. Is a statement, I'm holding a green marker and I'm holding a red marker, or sorry, black marker. Put that back down. Is a statement, I'm holding a green marker and I'm holding a black marker, true or false?
False.
False. Wonderful. And if I'm holding the black and not the green, is it true or false?
False.
False. And if I put down both markers, it's true, right?
No, it's false.
No, it's false. All right, wonderful. So that's the conjunction of two statements. You and them together. And here's how you determine the truth value of the conjunction. You look at the two statements, and depending on their truth values, you can determine the truth value of the conjunction. Make sense? Now we're going to do the same thing with disjunction. If A and B are statements, then the statement A or B is their disjunction. Once again, it has to be a statement, so we need to determine when this is true or false. And that little b right there is our symbol for or. So let's go over it. Set up the first scenario. We're doing the top row. So set it up. I'm holding a green marker. I'm holding a black marker. Is it true that I'm holding a green marker or I'm holding a black marker?
Yes.
It's false. And everyone else said true, and that's because we didn't talk about inclusive or versus exclusive or. So it's nice to have new students. So we use or two ways in the English language. We say that Donnie's in room 1 or Donnie's in room 2. Then you think, either I'm in room 1 and I'm not in room 2, or I'm in room 2 and I'm not in room 1. I can't be in both rooms at the same time. So in that sense, we're using what we call the exclusive or. An example of the inclusive or would be if I'm responsible for some university admissions, and I say, if you want to apply to my university, you have to take calculus or physics. Does that mean you can't get in if you take both? No, that's not what I meant. I meant it in the inclusive sense. I meant you had to take at least one. So we use or these two different ways in the English language, and it's somewhat ambiguous. And so when we use or in logic, we mean the inclusive case. We mean the university.
It can be both.
Yeah, both can be true. It means at least one is true. That's what we mean with or in logic. So now let's go over these one more time. So if I'm holding both markers, is the statement I'm holding a black marker, I'm holding a green marker, true or false?
True.
True. What if I'm just holding a black?
It's true.
What if I'm just holding a green?
It's true.
What if I'm not holding either?
False.
False. Good. Okay. Now, the negation. The negation of the sentence. Or a statement. So if A is a statement, then the statement A is false. Once again, we're calling this thing right here a statement. Is its negation. Another way that we might say A is false is we might just say not A. It's a faster way of saying it. So, let's look at all the cases. What are all the possible values that A can be? They can either be true or false. And if A is true, then the statement A is false is
False.
false. And if A is false, then the statement A is false is
True.
true. Now, an important note to make when we're talking about not is we're talking about the
Opposite.
contradiction. Come on, some of you guys just did this with me. Yeah, we're not talking about contrary statements. For those of you who understand, we're talking about the contradiction. If A is true, then not A, its contradiction has to be false. Contradicting statements. If I have two statements that contradict, one of them has to be true, and one of them has to be false. If I have two statements that contradict each other, I know that this one's false, then I know that this one's true. And if I know that this one's false, I know that this one's true. One has to be true, one has to be false. That's what we mean by contradicting statements. If A is true, its contradiction is false. If A is false, its contradiction is true. So let's look at an example of contradicting statements. So if I say A is a statement, all swans are white, then its negation, its contradiction, is some swans are black, right? Yeah, works perfect. No! What if you live in a universe with only orange swans? Is this statement true?
No.
Is this statement true? No! So we were not guaranteed that one of these was true and one of these was false.
Yeah,
So these are not contradicting statements.
There exists a
So
swan
I
that
say
is not white.
Not all swans are white.
Not all swans are white, right? Just put a not in front of it if you want to cheat, right? You want to say not A, just put a not in front of it. Real easy way to do it. Not all swans are white is a contradiction of all swans are white. Or another way we might say it is some swans are not white. That's another way that we can say that. So these two statements are contrary statements. Contrary statements are statements that can't both be true. Both these can't be true, right?
Right.
But they can sure both be false. So those are just contrary statements. Contradicting statements, one has to be true, one has to be false.
Right.
Feel like you got the difference there? Because that's all your homework is on from here on out. So do you understand? Okay, it's not really on the homework. Okay, so that's handling all that logic. Now we come back to here. So, what do we mean by equivalence? We mean, let me rewrite it this way. We mean, to say that A is logically equivalent to B, we mean A implies B and B implies A. So let's write that out. We mean A implies B and B implies A. That's what we mean, and then our shorthand notation for all this, because this is kind of a mess, is just A back and forth arrow with B. Make sense? So let's fill out this truth table. What are all my combinations?
True, false, false.
True, true, false, false.
Oh, okay.
True, false,
False, true.
false, true.
Okay.
Yeah, those are all the combinations. Alright, so true implies true is
True.
True.
true. True implies true is
True.
True.
true. Now notice that this is just a conjunction of these two. So we're just doing this and this. So true and true is
True.
True.
true. And then this one is just shorthand for whatever we put in this column, so this one's true. Good on that one?
Yeah.
Next one. False and false. False implies false is.
True.
I'm going to give you one more chance. False implies false is.
True.
Good job. Okay, and once again, false implies false is.
True.
So true and true is.
True.
And then this is just the same. Okay, next one. True implies false is.
False.
False.
False, right? That's the false one. If I say that my wearing shoes implies I'm wearing socks, and I am wearing shoes, I'm not wearing socks, then my implication is false. Right? Okay? And then false implies true is.
True.
True. False and true is.
True.
False.
False.
Oh.
Okay. We're lucky they corrected. About to rage. And then just repeat. And then the last one, let's see. False implies true is.
True.
True. True implies false is.
False.
True and false is.
False.
False. So there's our table. So what do we mean by A is logically equivalent to B?
Johnny, false implies true is, oh, false and true. Okay, that's where I was off.
Okay. So statement A is logically equivalent to statement B. There's our shorthand for it. If and only if A implies B and B implies A. Okay? So, really what equivalence means is A is logically equivalent to B if they have the same truth value. If they're both true, if A and B are both true, it's true. And if A and B are both false, it's true. This is only false if they have different values. Right? True is logically equivalent to true. False is logically equivalent to false. Is false logically equivalent to true? No. Is true logically equivalent to false? No. So it makes perfect sense that that's the way it comes out, right? So that's what we mean by logical equivalence. Now, so those are different logic operators. Last thing we need to talk about is vacuous, a statement being vacuously true. A statement being vacuously true, typically it's just an implication with a false, what? Antecedent, yeah. So if the antecedent on an implication is false, the whole implication is true. So if I start out a statement with, if Donnie's king of the world, then it doesn't matter how you finish it, it's always true, because Donnie's not king of the world. There's no cases to check, it's vacuously true. So if I say, so the statement, if Donnie's king of the world, the sun's raining water, it's true. Right? So that's what we mean by vacuously true. There's no cases to check. The example the author gives is, every perfect square integer that's also prime is negative. There are no perfect squares that are prime. Because if it's a perfect square, it's definitely not prime. So there's no cases to check. So that's what we mean by vacuously true. So that's the end of that. That's everything that we had to cover today. Pretty nice, simple, easy day to begin with. It's whatever time it is. So what we're going to do, you guys are going to be able to do your homework from here on out. Well, I'm doing it for you the first time, and this is really risky. Don't abuse this. Don't be stupid. If you are stupid, it's going to come back to bite you in the long run. I'm going to give you homework solutions to begin with, so that you can do your homework, and you can check your homework against the solution, so that you can get a feel for what kind of expectations I have for how you do these problems, and to help you get comfortable as we go. Do not just take this and rewrite this as you go. First off, it'll be obvious if you're writing it how I would write it versus how you would write it. Right? And second, that's not going to help you. Try to solve the problem yourself. Use this when you feel like you can't figure out how to do it, you're getting stuck. Don't give up in the first 2 minutes or 3 minutes. Really try the problem. And then this is for you to fall back on. Okay? So I'm only doing this to begin with to help you get going, because a lot of students, they didn't feel comfortable, like they knew what the answer was, they just weren't sure how to give it to me. Oh, second thing for any of you who have just terrible handwriting, if I can't read it, it's a 0. I had bad handwriting when I went to school, which is why I had to type up my solutions like this and give them to my teachers. Yeah, that's how this exists. I wrote these when I went to school. And they might also have mistakes because of that. So, if you can't, start typing. And I guarantee you, you'll figure out that you can write so that I can read it. After trying to write, because writing math is a stupidly slow process. So, here's your solutions. Don't just write out the solutions. Actually try to solve the problems. Use it as a fallback to help you understand. And then, obviously at the beginning of each class, maybe you have my answer, and my answer for some reason doesn't make sense to you. You're still welcome at the beginning of class. Just because you have the right answer doesn't mean you don't have questions about the problem. I'm happy to spend any time you have on questions with problems. Make sense? All right, so go on break, and after that you can start work on your homework. And this is the only lecture that's going to be this short, just so you know.